Hello students, welcome back to JCE Connect series of lectures. So in this particular lecture, I will be starting module number 3, Open Channel Flow Hydraulics, that is a non-uniform flow. So in previous module also we have studied open channel flow hydraulics, but there we have been studied the uniform flow through a channels. There we have studied the various types of flows, G's equation for uniform flow through a channel. Then we have been derived most economical channel sections, uh, conditions for most economical channel sections, the energy concept in channel sections by considering a uniform flow. In this particular module, you will be studying about a non-uniform flow. These are the contents of non-uniform flow. So here you will be studying about a non-uniform flow, how the non-uniform flow takes place in a channel, what is the parameter going to change while flowing, then hydraulic jump, how the hydraulic jump takes place, and what are the conditions for hydraulic jump, what are the practical applications of hydraulic jump. These all aspects you will be studying in this module. And even for conjugate depth calculation and energy loss calculation due to hydraulic jump, then the numerical problems on hydraulic jump, then the gradually varied flow, in the equation for gradually varied flow, then the backwater curve and afflux. uh, what do you mean by backwater curve, then or what do you mean by afflux, you will be studying in this module. Then the description of water curves or of profiles, like a mild profile, a steep profile, critical, horizontal, and adverse slope profiles. Then the numerical problems on identifying the flow profiles. So these are the contents given in a syllabus. You will be studying in a non-uniform flow these many contents. So first, let us study about the uniform and non-uniform flow. Already you know about uniform flow. What do you mean by uniform flow? And non-uniform flow definition, you know it. And once again, I'll repeat the things here. The uniform flow means it is the flow in which the condition of flow remains constant from section to sections. So means if the discharge is passing through a channel, if the channel cross section is remains constant, or the depth of flow is remains constant throughout the length, then the velocity will be remains constant. That particular flow what we call as a uniform flow through a channel. Even if the diameter of the pipe is remains constant, whatever the discharge is passing, it will be passing with a constant velocity, and that particular flow is also being called as uniform flow. And what do you mean by non-uniform flow? The non-uniform flow means it is the flow in which the condition of flow does not remain constant from section to sections. So let us see this figure. In this figure, if you look at this figure here, this section or this section, it's a varying duct, or you can call it as a varying channel section. The depth is not same throughout the length. As the depth is not same, the velocity will be varying, because velocity is inversely proportional to depth of flow. In this condition, if you take wherever the section, the depth will be remain same. So if depth is remains same, the velocity at every section will be the same, means velocity remains constant. In this particular figure, so that it is a variable channel section. The area is not constant, or you can say it is the depth is not constant throughout the length, hence the velocity get varies. Hence we can write dou v by dou x is not equal to 0. This particular type of flow what we call as a non-uniform flow through a channel. So in this particular figure you can observe here, so which is the non-uniform flow and which is the uniform flow. So here this is the obstruction and the water is flowing in this direction. The flow which approaches the obstruction, so look at this on the upstream side, this will be upstream side and this is downstream side. The flow on the upstream side before approaching any obstruction, the flow was uniform, means the depth of flow remains constant, and as it approaches any obstacles or obstructions, then the depth gradually starts varying. Gradually it starts varying, then it passes over the obstacle and suddenly falls down, and here the sudden change in the depth of flow will be taking place. And on the downstream side, the moment it falls down, then it starts whirling like this. Then at within a short interval of time, the depth will be varying. In this particular section you will be getting a rapidly varied flow, and here you will be getting the gradually varied flow. Both gradually and rapidly varied flow are being classified as a varied flow, and rapidly varied flow and varied flow will represents non-uniform flow. So this on the downstream side of flow will represents the non-uniform flow. It means the depth of flow will not be same throughout the length, means up to certain length it will vary gradually the depth, and then it becomes uniform flow later. But these gradually varied flow and rapidly varied flow both will represent the non-uniform flow. So you can see here where you can get the uniform and non-uniform flow. So uniform flow means the depth of flow will be same, the velocity will be same, and non-uniform flow means the depth of flow is not same and the velocity will be variable, but the discharge passing is remains constant. Irrespective of the depth of flow, the discharge will be remains same. Even in uniform flow also the discharge will be same, but passing with a constant depth of flow. That is called uniform flow and non-uniform flow. Then next, so why where the non-uniform flow will take place or how it will be taking place? In non-uniform flow, velocity varies at each and every section of the channel, and the energy line is not parallel to the bed of the channel. Means in a uniform flow, if you take a uniform flow here, if you take a uniform flow, at every section the depth will be same, and in uniform flow the slope of the bed, the slope of the water line, and the slope of the energy line, if you draw the slope of the energy line, the slope of the water line, and the slope of the bed, all will be parallel to each other. When they all will become a parallel to each other, and that flow what we call as a uniform flow. But in case of non-uniform flow, since the depth of flow is not constant at every section, the velocity get varies, then the energy line will not be parallel to the bed of the channel or slope of the water. So it will be obviously varies. So that is, in a non-uniform flow, velocity varies at each and every sections of the channel, and energy line is not parallel to the bed of the channel. This can be caused. Why that non-uniform flow will takes place in a channel? The reasons are differences in depth of channel and differences in width of the channel. This is first one, differences in the depth of channel. Because of the varying depth, the velocity will not be same, and because of the differences in the width of the channel, because of the differences in the nature of the bed, and because of the differences in the slope of channel, and also because of obstructions in the direction of flow. So anything may come uh, uh, across its flow. The flow may get suddenly drop, or the flow may get suddenly hump, Because of these conditions, the non-uniform flow will take place in a channel. So because of the obstruction, it may take place non-uniform flow. Because of the obstructions like a drop or a hump, the depth of flow get varies, or because of varying the width of the channel, then the depth may get varied, or because of the nature of the bed, the non-uniform flow may take place. Then because of the changing in the slopes of the bed, the non-uniform flow may take place. So these are the conditions to get non-uniform flow in a channel. Next, so look at this figure. You will completely understand what you mean by uniform flow, and where the gradually varied flow takes place or where the rapidly varied flow takes place. So try to understand the types of flow here. So you'll be having a two types of flows. One is a uniform flow, other one is a varied flow. In a varied flow, you'll be getting a two types of flows: gradually varied flow and rapidly varied flow. Those are being represented at GVF. GVF means gradually varied flow, RVF means rapidly varied flow, and UF means uniformly varied flow. So if you understand that where the gradually flow takes place or where the rapidly flow takes place, then you can easily understand what you mean by the non-uniform flow. So here given the presence of an obstruction in a channel, such as a gate or a change in a slope or a cross section, causes the flow depth to vary. That is called varied or non-uniform flow. I'll repeat. uh, the presence of an obstruction, I explained earlier, obstruction, it could be a drop, it could be a hump in the channel, such as gate or a change in a slope or cross section, causes the flow depth to vary. Then it is called as a varied flow or a non-uniform flow. Such a varied flows are common in both natural and human-made channels. Natural means a river, a stream. It is common, quite common, and in human-made channels also it is present. Open channels such as rivers or irrigation systems and sewer lines. Then what do you mean by rapidly varied flow? If the flow depth changes suddenly or markedly over a relatively a short distance in a flow direction, such as the flow of water past partially open gate or over a falls, it is called as a rapidly varied flow. And gradually varied flow means if the flow depth changes gradually over a long distance along the channel, it is called as a gradually varied flow. Then a gradually varied flow region typically occurs between a rapidly varied flow and uniform flow regions. Just look at the figure here. I'll show you here in this figure, particular figure here. See, up to here it is been shown uniform flow. Means wherever you take here, here or here, the depth was same and it was representing as a uniform flow. Then as it approaches the obstacle or obstruction, this is the obstruction made in a channel. This obstruction is nothing but a drop. This is the drop in a channel. Because of the drop present in a channel from uniform flow, it started varying gradually. The depth started varying that gradually. This is called as a gradually varied flow. The moment it falls down, it will be having a huge kinetic energy while falling. The moment it falls down, the depth varied rapidly. If you take section here and section here, in these two particular sections, the depth will be varying very rapidly. Hence, it is called as a rapidly varied flow. If you take a section 1, 1 and section 2, 2, I'll erase this one. If you take a section 1 here and section 2 here, you can observe the depth is less here and the depth is more here. And between these two sections, whatever the flow condition is there, this flow condition what we call as a rapidly varied flow, and also this particular condition what we call as a hydraulic jump. And about this hydraulic jump we'll discuss later. And when the flow changing from rapidly varied, or when the flow changing from supercritical to subcritical, you know about the supercritical means very uh, high speed water to low speed water. When the when the flow takes place from supercritical flow to subcritical flow, supercritical means the depth of flow will be less but the velocity of flow will be high. Subcritical means the depth of flow is high, the velocity will be uh, low here. Okay, from high velocity to low velocity. So this is called rapidly varied flow. So in this particular uh, section, so the non-uniform flow will takes place, and the gradually varied flow generally is in between rapidly varied flow and a uniform flow. Okay, so I hope you understood this one. I'll repeat. The presence of an obstruction in the channel, such as a gate or a change in the slope or a cross section, causes the flow depth to vary. That is called non-uniform flow. Okay. Then, so here the difference between uniform flow and non-uniform flow. So already explained about that one. You can see the difference here. If the flow velocity at a given instant of time does not change within a given length of a pipe or a channel, then the flow is called as uniform flow. If the flow velocity at a given instant of time changes within a given length of the pipe or a channel, then the flow is called as non-uniform flow. So in exam, if they ask what is the difference between uniform flow and a non-uniform flow, you can write if the flow depth remains constant throughout the length of the channel, hence the velocity will remains constant, then the dou v by dou x is equal to 0. That means the velocity is constant. That flow is called as a uniform flow. If the flow depth is not constant throughout the length of the channel, hence the velocity get varies, hence the dou v by dou x is uh, sorry do in uniform flow the dou v by dou x is equal to 0, but in non-uniform flow the dou v by dou x is not equal to 0. And you can draw the figure and show of where you get the uniform flow and where you get the non-uniform flow. So here in this one you will get a dou v by dou x is equal to 0. Here you get dou v by dou x not equal to 0. Means if the velocity varies here the velocity will be constant. Then next comes very important thing, the hydraulic jump. What do you mean by hydraulic jump? So it's very important in a hydraulic structures. uh, the hydraulic jump needs to be designed. You have to make to jump a water, and you have to design the hydraulic jump. Then what do you mean by hydraulic jump here? In an open channel, when a rapidly flowing stream abruptly changes to slowly flowing stream. I'll repeat, in an open channel flow, when a rapidly flowing stream abruptly changes to slowly flowing stream, a distinct rise or jump in the elevation of a liquid surface takes place. This phenomenon is known as hydraulic jump. Again, the hydraulic jump converts kinetic energy of rapidly flowing into a potential energy. Then due to this there is a loss of kinetic energy. The hydraulic jump is also known as a standing wave because it is in essence a wave which is a stationary at one place. Means when it get converts from kinetic energy to means high flow uh, high velocity flow to low velocity flow, suddenly the flow get slow down. Then at one particular point it becomes stationary, and that particular situation is called as a standing wave condition. Then the rise of water level in which place in which the rise of water level which takes place due to the transformation of the supercritical flow to the subcritical flow. So these are the some of the definitions where the hydraulic jump can generally occur, or you can define the hydraulic jump in this particular form. But I'll show you what do you mean by hydraulic jump. So look at this figure. See here a dam. Here I'm showing the dam. So this is a dam. The flow behind a dam. Look at up to here. The before approaching the dam, the flow 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 was uniform flow. As it approaches the dam, then slowly the depth started varying. Then this varied depth flow is called as gradually varied flow. The moment it falls down from the crust of the spillway, this is called the dam spillway, it will be having a huge kinetic energy. This will be having a huge kinetic energy. And the condition of flow here, it is called as a supercritical flow. At this particular flow, where the kinetic energy is very, very high, the Froude number, if you take, it will be less than, sorry, the Froude number will be greater than 1. If you take, it will be greater than 1. If you take greater than 1, means it's a condition of flow is supercritical. It is flowing from steeper slope, and suddenly the flow will be uh, coming in contact with the flatter slope here. The moment it comes and contact with the flatter slope, suddenly the energy get decreases, means from kinetic energy to potential energy. It is converting from kinetic to potential energy, means if you take a depth here, it is very less. Suddenly when the energy is being uh, reduced from kinetic to potential, then the depth of flow increases here. Then that condition what you call as a hydraulic jump, means the flow changing from supercritical flow to subcritical flow, from the lower depth of flow to higher depth of flow. So earlier at the lower depth of flow, where the kinetic energy was very, very high, then the moment it comes in contact with the flatter slope, then suddenly the depth of water get increases, then suddenly the energy get reduced. Then that condition what you call as a hydraulic jump. You can look here. So hydraulic jump, the moment it comes and suddenly it jumps like this, and here if you take, the flow is higher, and the depth of flow is very higher, depth of flow is very less here. That's why it is given here in this previous slide. What is given here, the rise of water level. Here I show this one. Look at this point. The rise of water level which takes place due to the transformation of supercritical flow to subcritical flow. Even the hydraulic jump converts kinetic energy of rapidly flowing into potential energy. Okay, so here that is showing here. See in this particular figure, so here the water falling down, which is having a huge kinetic energy, when it falls down suddenly it jumps. Then for that jump, it means the kinetic energy get converting into potential energy. Okay, this is called hydraulic jump. Or let us take one more condition here where you get a hydraulic jump. So let us take, this is the sluice gate. Okay, this is the gate provided here. So this is the water behind the gate, the water behind the gate. When you open partially this gate, just you lift it up. Okay, this gate you lift it up. When you open this gate, earlier the flow was subcritical, means the depth of flow was high here, the velocity was less here. The moment you open the gate, when you open the gate, suddenly the flow becomes first critical, means it will come down slowly, then it becomes lower than the critical flow, then suddenly it passes with a very high speed. If you take a channel, as I explained, the critical flow, subcritical flow and supercritical flow, in a channel if you take, and this if you assume it is a critical flow, the flow above the critical represents subcritical flow, means low velocity, and the flow below the critical represents supercritical flow. The velocity will be very high, and here the velocity is less here. Then when it becomes subcritical to critical, then critical to supercritical, and it will be giving you the very high energy, and this flow represents the shooting flow. It shoots out and comes with a very high speed, and that particular flow is called a supercritical flow. When it meets to the uh, surface here, again it's gradually it goes on increasing. From here onwards it started increasing, the depth increases here, means from high velocity flow to low velocity flow it becomes in these two particular regions. Then the whatever the condition of flow we get, that is called as a hydraulic jump. Then after taking hydraulic jump, gradually again it flows and again it falls down, then it moves forward like this. Okay, so you remember the hydraulic jump means the flow from the supercritical to subcritical. When the flow takes place from supercritical to subcritical, that is called hydraulic jump. Then look at this figure, you can understand where you generally get the hydraulic jump. So here given, flow under a sluice gate accelerates. We'll take this one. See, flow under a sluice gate accelerates. This is the sluice gate, this is the gate provided here, and this is the tank, this one is a tank. The flow under a sluice gate accelerates from subcritical to critical. It means since the depth of flow here is high, as the depth of flow is high, the velocity will be very low. If you take it one particular section, the flow is critical. So this represents critical flow, where the Froude number will be equal to 1. If you take above critical, the Froude number will be less than 1. Then the Froude number less than 1, it represents what? Subcritical flow. When you open the gate, here is this one, when you open the gate, when you open this gate, then the flow starts coming out like this. It starts coming out, it comes here, then it comes here, then it comes down the critical flow, means it is changing from subcritical to critical, then critical to supercritical. That is given here. The flow under a sluice gate accelerates from subcritical to critical, then from critical to supercritical, and then jumps back to subcritical. Then when it comes down, it will be shoots, it comes with a very high velocity, high kinetic energy. It will be having a very high kinetic energy. And here here you to take the depth is lesser than the critical, and here the Froude number, if you take, it will be more than 1, means it is changing from supercritical to subcritical. Again, if you take a depth here, it will be more than the critical, hence this flow represents the subcritical. When the flow changing from supercritical to subcritical, then the hydraulic jump will takes place. While while getting hydraulic jump, the water starts whirling here. Okay, so this is what we call as a hydraulic jump. So remember, the flow when changing from supercritical means low depth low depth of water, which is having a huge kinetic energy, changing from huge kinetic energy to uh, uh, low kinetic energy or the potential energy. Okay, so it is the flow changing from supercritical to subcritical is called as a hydraulic jump. Okay, so this particular reason represents the hydraulic jump. Okay, this is a low depth, this is the high depth. This here we get a subcritical, here we get the supercritical. So whenever you open the gate, the water will coming with a very high velocity, or it will be having a huge kinetic energy, very huge kinetic energy. Then suddenly the depth get increases on the downstream side, then from supercritical to subcritical, then the hydraulic jump will takes place. Or if any obstruction, if you are getting any obstruction like a dams and all, if this is the channel, if you are getting any dams and water is flowing down, then suddenly the jump will takes place there also, the hydraulic jumps takes place. Okay, this is about the hydraulic jump. This is very important concept in a non-uniform flow channel sections, and we will be deriving the equation for hydraulic jump later. So try to understand the definition of hydraulic jump. So again I'll repeat, hydraulic jump will takes place uh, here and here. Then with this length, what we call the length of hydraulic jump, then whatever the depth at section 1, this is take at section 1, this is you take section 2, whatever the depth at section 1 we get will be the lower than the critical depth. Let us call this depth at 1 will be y1, depth at 2 will be y2. Y1 will be the lesser than the critical depth, and y2 will be the more than the critical depth. But the discharge whatever is passing will be remains constant, and this discharge we will be passing with two two depths, and these two depths are been calling as a conjugate depths or alternate depths, or these depths are been called as a sequent depths. So this we have studied in uh, energy curve. When we have been drawn this enemy, you think you might have uh, studied this one, you have studied this one, this curve. Repeat this one, this curve, about this curve we have studied. So one curve was passing, that is energy in energy concept. This is one more curve, the resultant of two were this one, and at that one particular point we were getting the minimum energy corresponding to the minimum energy, whatever the depth we were getting the critical depth, and above critical depth whatever the depth we were getting, that is subcritical flow condition, and below critical whatever we were getting, that is supercritical conditions. Okay, leaving this particular point wherever you are taking the depths, so at a constant discharge you will be getting two alternate depths, and we have been solved some of the problems on this in previous module. Okay, so likewise, so here also we will be solving the alternate depth problems, and this is one depth and this is one depth. Okay, remember this definition and condition where the hydraulic jump will takes place. And this is also represents the hydraulic jump here also. Hydraulic jump is a local non-uniform flow phenomenon resulting from the change in flow from supercritical to subcritical. If you take this steep slope here, steep slope, where the depth of flow if you take here, it is very less, it is a below critical, then it shoots, the velocity will be having very high, hence it possesses a huge kinetic energy. Then the moment it comes and contact with the flatter slope here, if If we come in contact with a flat surface, suddenly the depth get increases. Then the kinetic energy is been killed here, means the dissipation of energy takes place. That is from supercritical flow to subcritical. While dissipating the energy, it will jump like this. Then that particular flow, what we call that particular jump is what we call as a hydraulic jump. In a hydraulic jump, there is a discontinuity in the surface characterized by the steep upward slope of the profile accompanied by the lot of turbulence and eddies. The eddies cause the energy loss. Means, so while jump when the jump takes place, the turbulence will be creating here. Then that those turbulence is called as a eddies, and the eddies will create the losses, that is called energy loss. And the depth before and after the hydraulic jump are known as conjugate depths or sequent depths. If you take in this particular here, in this particular figure, the depth before the jump means here the represent as a y1 and velocity is v1 here, and the discharge passing through here is q, and after jump the depth is y2 here, and the discharge passing also q, means the discharge can be passed in two depths, one passing by having a lower depth higher velocity, and another one is higher depth lower velocity. Then the energy get it loses certain kind of energy here, that is called energy loss. And in next part we will be deriving the equation for hydraulic jump. What are the conjugate depths? There is a y1 and y2 we will be calculating. Then the energy loss also we are calculating, and what is the length of jump also we are calculating. So in this particular section, try to understand what we mean by hydraulic jump and where it takes place. Okay. So in this particular section also it has shown the hydraulic jump here. If you take this one, which represents the hydraulic jump, here I have shown the spillway crust, and behind this behind the dam, if you take this particular things indicates the dam, the flow behind the dam, which represents up to certain length, it is uniform flow, and as it approaches gradually varied and falls down, it will be having a huge kinetic energy. Then it jumps like this is called hydraulic jump. So because of hydraulic jump, some energy loss will takes place because of the creation of eddies or the turbulence on the downstream side of the flow. And this hydraulic jump will be must in hydraulic structures. We need to create a hydraulic jump. For creation of hydraulic jump, certain design procedure will be there. We have to have a hydraulic jump, and why to have a hydraulic jump, and what is the application of hydraulic jump, we'll see in the next part of this lecture. Okay, but the jump will takes place when the flow is from supercritical to subcritical. That is what we call as a hydraulic jump. I hope you understood this concept of hydraulic jump. So let us discuss about the practical application of hydraulic jump. So here the practical applications are: engineers design hydraulic jumps to reduce the damage to structure and the stream bed. Means, if you take this particular dam section here, when the water is flowing over the dam, as I said, it will be having a huge kinetic energy here. The moment it falls down, as it okay, then if it flows with a very huge kinetic energy, having very high velocity of flow, then it may scour the bed, it may erode the bed. In turn, it affects the stability of the structure. We have to prevent from the bed we have to prevent the bed from the erosion of the flow. To prevent the erosion of bed, we have to create a hydraulic jump. So after falling down, the water has to jump and then it has to move. Hence we can prevent the bed of the channel as well as bed and banks as well as the hydraulic structure. Okay, so uh, how it can be made, a stilling basin will be provided on the downstream side of the dam or a weir. Here a stilling basin means it will be having a certain depth of water and the water will be falling on the water. If water is falling on the water means there won't be any erosion of the bed or banks takes place. The water is directly falling on the water, then it jumps and it moves like this. So this is what the practical application of a hydraulic jump. So here it is been given as engineers design hydraulic jumps to reduce the damage to the structure and the stream bed. Proper design can result in a 60 to 70% energy dissipation. So it can dissipate 60 to 70% energy by creating the hydraulic jump on the downstream side of the dam or the weir. So what is the second application? It minimizes the erosion and scouring due to high velocity. As I explained, it will be having a huge kinetic energy and it is moving with the same energy. It may scour or the erode the bed and banks of the channel. Hence, in turn, it affects the stability of the structure. So by creating the hydraulic jump, we can prevent the erosion and scouring due to high velocities. So that is in case of a dams, weirs and other hydraulic structures. So next is, then again some of the again applications as an energy dissipator to dissipate the excess energy of the flowing water downstream of hydraulic structures such as a spillway and a sluice gates. The hydraulic jump can be created. Mixing of chemicals in some chemical industries, to mix the chemicals, this hydraulic jump concept will be using. Then the aeration of stream polluted by biodegradable wastes, there also the hydraulic jump concept will be using. Then the rising the water level in the channel for irrigation purpose, sometimes this hydraulic jump can be used to raise the water level in the channel, then later it can be feeding into the irrigation channels. Then the desalination of seawater, uh, to remove the salt content present in the seawater, the hydraulic jump concept can be using, and efficient operation of flow measurements in the flumes. So there the hydraulic jump concept will be using. So you look at the figure, this you might have seen on the downstream side of the dam, this one. So how the hydraulic jump is being taking place? So here it will be having a huge kinetic energy flowing on the spillway of the dam. It will be having a huge kinetic energy as it passing with the same energy. One here also it may scour or they erode the bed and banks on the sides. So when it bed and banks started eroding because of having a huge kinetic energy, in turn it affects to the stability of the structures. So to prevent the erosion of the bed as well as the banks, so the hydraulic jump is must. So we need to create a hydraulic jump. For this hydraulic jump there is a certain design concept we need to study and make a water to jump. Okay, so this is what we call the hydraulic jump. This is hydraulic jump, the flow from supercritical to subcritical. Here the depth is more, here the depth is less. Okay, here the flow is supercritical, here the flow is subcritical. When the flow is from supercritical to subcritical like this, okay, here if you take here the depth will be varying. Okay, this is called hydraulic jump. I hope you understood this concept of hydraulic jump. So we'll derive the equation later. Next, classification of hydraulic jump. So based on the Froude number, we know the Froude number, that is a Froude number equal to 1, that is called critical flow, then less than 1 subcritical, greater than 1 supercritical. Here it is given, if the Froude number is less than 1, jump is impossible but violate the second law of thermodynamics. Means if Froude number is less than 1, it is not possible to have a jump. If Froude number is between 1 to 1.7, a standing wave or or jump about 4 times of y2, long jump will takes place and the low dissipation of energy, that is less than 5%. If the Froude number is between 1.7 to 2.5, the smooth surface rise with a small rollers known as weak jump, dissipation of 5 to 15%. If the Froude number is between 2.5 to 4.5, if you are getting, this is represent unstable flow, oscillating jump. Each regular pulsation creates a large wave which can travel downstream for a miles, damaging the earth banks and other structures not recommended for a design condition. Means if you are getting Froude number 2.5 to 4.5, that condition represents, you can decide based on the Froude number what type of condition of flow you may get. Here it is given the condition of flow. If you while designing, if you calculate the Froude number, if you are getting a Froude number between 2.5 to 4.5, then it represents unstable flow. How the flow takes place? Oscillating jump it takes place. Then each regular pulsation creates a large wave which can travel downstream for a miles, then started damaging the earth banks and other structures, and it is not recommended for the design conditions, and the dissipation of energy takes place 15 to 45%. If the Froude number is 4.5 to 9, a stable, well balanced, steady jump is taking place in, but it is stable, but in previous case the jump was unstable. When you are getting a Froude number 4.9, which was giving you a stable jump, well balanced, steady jump, best performance and action, insensitive to downstream conditions, best design range, dissipation 45 to 70%, and these are being tested practically and given these numbers, whatever the based on the Froude number, whatever the jumps are being classifying, these are practically tested and given. Uh, okay, then if the Froude number is more than 9, rough, somewhat intermittent, strong jump but good performance, dissipation of 70 to 85% energy. So we need to dissipate energy here, otherwise what happens, as I said, the erosion of bed and banks will take place. As the bed and banks get erode, it will affect to the stability of the hydraulic structures. So we need to kill the kinetic energy of the water as much as possible. Then next, here you can clearly see how the jump will takes place, and this is a classification of jump. In this one, the first figure A represents classification of hydraulic jump here given. When the Froude number is equal to 1 to 1.7, undular jumps will take place. Just look at the figure A, the jump is undulating. This is showing the undular jump. Then Froude number is between 1.7 to 2.5. It is a weak jump. Figure number B represents the jump is weak. And figure C, that is Froude number is between 2.5 to 4.5. The jump is oscillating jump. It is oscillating. That is figure number C. And Froude number is 4.5 to 9. The jump is a steady jump. It is good, and dissipation of energy will be more 45 to 70%. And the Froude number is equal to 9 or greater than 9, then it will be a strong jump, and it is also recommended for the design. These are the some classification of hydraulic jump. So please study about these things and try to understand what do you mean by hydraulic jump. And hydraulic jump is being classifying based on the Froude number, because the Froude number is a function of Froude number, if you take is a function of depth and velocity. Depth and velocity, because Froude number equation, we know the Froude number equation as V divided by root of Gy, where G represents acceleration due to gravity. This acceleration due to gravity we get because of having a slope, and because of the slope, the depth of flow get decreases, velocity get increases. Okay, so since the Froude number is a function of depth and velocity, and based on the Froude numbers, the jump can be classified as explained earlier. Okay, so how the jumps will take place: strong jump, weak jump, undular jumps, steady jump. So these kind jumps are required in a hydraulic structure just to prevent the hydraulic structures from the erosion of the bed and the banks. These jumps are must. We need to study about the jump, and we have to calculate the equation for the jump, the depth for the depth before the jump and depth after the jump, then the length of the jump, how much energy is dissipating. These all things we need to calculate for the any hydraulic structures. So I hope you understood about these things. This is the introduction about the non-uniform flow. Okay, then this is the hydraulic jump. So as I given the introduction part about the non-uniform flow, so again the non-uniform flow means the depth of flow will be varying throughout the length of the channel. The velocity is not constant. The velocity is not constant. That type of flow is called as a varied flow, that is called as a non-uniform flow. uh, then we have studied where the non-uniform flow we get if any obstruction uh, we get in along the direction of flow, then the flow becomes a non-uniform. Then the hydraulic jump, about the hydraulic jump, where it takes and how it takes, what are the application of hydraulic jumps, we have studied in this particular part. Then we have studied the classification of hydraulic jump. So we have been classified hydraulic jump based on the Froude number, that is undular jumps, weak jump, oscillating jumps, steady jump, then the strong jump. These are been classified based on the Froude number. So I hope you understood this one. So please study these things, and in the next lecture I'll be deriving a equation for hydraulic jump. Okay. Thank you.